Good afternoon. Welcome to the Student Faculty Seminar and the Philosophy Forum. It's my pleasure this afternoon to introduce Roald Hoffman. He is Professor Emeritus of Chemistry at Cornell and also the Frank H.G. Rhodes Professor Emeritus of Humane Letters at Cornell. Regarding Professor Hoffman's accomplishments, let me say this. When you consider your own ambitions in the light of his accomplishments, you're not sure whether to be inspired or depressed. As for me, I've been inspired. And so will you be this evening at 8 o'clock in the Denison Theater, when you will get a full account of Professor Hoffman's career, and when he will talk about the commonalities and differences between the arts and the sciences. However, let me give you a hint if a hint is needed. In 1981, Professor Hoffman received the Nobel Prize in Chemistry. And his talk this afternoon is about 2 new games for carbon. Please help me welcome Professor Hoffman.
So this is a pretty straight chemistry talk, though there are philosophical issues that will emerge perhaps along the way. Not only is it a straight chemistry talk, but it is a talk which I think there is not a single orbital that appears in here. So it's not because I don't like orbitals, but there's something else going on here. Several threads for those of you who know my work. One is how does a person who loves and subsists on qualitative notions in chemistry, explanations, which involved orbitals, how does he survive in a time of computational chemistry when numbers are the meaning and simulation? So that's one subtext here. And the other is of retaining a love for chemistry. So there are 2 subjects. They're both papers that were published this last year. They have, carbon is the relationship between the 2. And the first one is about nanothreads. So nanothreads, the ones I'm talking about, are completely saturated, one-dimensional benzene polymers. And you may be able to see the benzene C6H6. They have a composite in them, or you may not. You'll see it a little bit later in another way. So this comes about from a grant that we're in on, which is really to the Carnegie Institution of Washington, who are major players in a high-pressure community, and this has something to do with high pressure. And in turn, there is a subcontract to Penn State and to Cornell. And at Penn State there are 2 groups, one in chemistry and one in physics. And it was interesting that President Engstrom's son just finishes the PhD degree, as it happens, with the person with whom we're collaborating in here, and with whom we've just written a paper, which is down here. It was probably his first paper in JACS, the physicists. And in our case, we're interested in the mechanisms of formation, theoretical side, and the action is one postdoc, Bo Chen, who is very talented. So the story has to do with benzene. And benzene, of course, is an archetypical molecule for chemistry. I picked here in an old bottle where the name is in German, as you can see, benzol. because in the story is at its origins, and it's the fascinating story of the structure of benzene elucidated in the decade of the 1860s by Kekulé and by others, and I am not going to talk about the Ouroboros dream of Kekulé, which is behind that or connected to that, nor am I going to talk about much about benzene in terms of why it plays this archetypical role in chemistry. It's a low melting solid, it's a liquid at room temperature, it's not particularly healthy. It's a good solvent, but it's not particularly unhealthy. Not on the scale of things, it's okay. What I am going to talk about is high pressure. So this is a cultural referent. In Europe, I wouldn't have to explain it, but in America, professors don't read asterisks, but their children do. And so this is Obelix applying some high pressure to some Romans. The benzene has been studied under conditions of high pressure for just over a century. This is quite remarkable. So here is a paper by Percy Bridgman, who is a great pioneer of high pressure research at Harvard. And in this paper, he says the phase diagram of 11 substances is a special reference to the melting curve. He took 11 substances off the shelf, not quite off the shelf, because he actually refines the benzene. He says he takes the purest benzol. He calls it by the German name still there. Interesting. He purifies it by distillation, by crystallization, by redistilling it. He's very interested in getting it pure. And then he's subjected to high pressure. The pressure that he was able to attain at that time was of the order of about 10,000 atmospheres or so in his apparatus. The experiments that I'm going to talk about, which the Penn State people did, we had no part in them, involve pressures which are of 200,000 atmospheres. So these are these are way beyond what your chemical engineers, you can buy a pressurized vessel to run a liters on 100, to run 100 liters of stuff at 200, 300 GPa pretty cheaply. So that's routine stuff. This is not routine stuff. It's done under different experimental conditions, but it's still possible laboratory work. It's done by squeezing between diamonds, either single crystals or polycrystalline in this case. This is a special kind of press. It's, as you see, it's about half a meter across or so. There are two diamonds. The squeezing is actually done between the diamonds. The general principle is the elephant's foot principle. I mean, there's a force per unit area. The smaller you make the area, the higher the pressure that you get. And this, it's called a Paris-Edinburgh, sir. It's an Oak Ridge laboratory. And they compress this to 20 gigapascals. That's the unit. 1 gigapascal is 10,000 atmospheres. So 20 times what Bridgman had. And then the key was that they did what anyone in their sense who would be doing a synthetic procedure should do, and which metallurgists could tell them that you have to do, is you have to anneal, you have to do things slowly. You don't just quench the thing. If you quench the thing, you're going to get a glass, an amorphous solid, cracks, everything else. So they decompressed it slowly for the first time in 100 years, it seems, because until then, people who had compressed benzene found that it undergoes a series of phase transitions and then turns into a white amorphous solid, which is returnable to atmospheric pressure and is totally intractable, except it analyzes CH, like benzene, but it dissolves in nothing. and it's hard to get information on it. They got a material, they did a slow decompression over 10 hours, which is not terribly slow, and they got occasionally some glassy looking stuff that looks like that. It's still amorphous looking overall, the morphology. Sometimes it was whitish and sort of thread-like, and they decided to look under a scanning tunneling microscope in it, and what they saw was this material over here. They saw threads of it, and when they sonicated this, they could see the actual, to disrupt the structure here, actual little tubules that you see protruding over here. But now the scale is what's really incredible, because that's 10 nanometers. 1 nanometer is 10 angstroms, so that's 100 angstroms. And so this is a scan across that bar, and you get a 6.4, the striations are 6.4 angstroms. So these are now molecular scale. And the contrast, you may know about nanotubes. There are beautiful pictures of nanotubes. But if you actually look at the material, it does look like a bunch of spaghetti, and so does this. This is some later. These are the nanothreads. These are nanotubes. Nanotubes are pure carbon, essentially curled up graphite, very interesting properties. But look at the scale. This is 1 micron. 1 micron is 1,000 nanometers. So this is 10 nanometers. So you're down here. These things are down a factor of 40 to 100 from the typical nanotubes in thickness. So they're very thin. They're thin on a molecular scale, and that's about what a benzene ring is across once you add the van der Waals radius to it. So actually that was part of the story. Now they threw at this every technique of characterization that you can do to an amorphous material. It doesn't dissolve in anything, so you can't do an NMR, okay? It's not crystalline, so you can't do the crystal structure, but you can do diffraction, and they did both neutron and X-ray diffraction, and you can do an analysis. It analyzes for CH approximately. You can also do C13 solid state NMR on this. And this is the region of sp cubed, like 4-coordinate carbon. This is 3-coordinate carbon. It's mostly 4-coordinated. There's a little bit 3-coordinate. And the most informative actually is Raman on this. And those Raman structures are very characteristic of saturated individual hydrocarbons which have CH groups on them and which have 6-membered rings. So here is the achievement of the Penn State group. For the first time in 100 years, there is something somewhat ordered coming out from the compression of benzene. And the decompression, slow decompression is the key. There are one-dimensional nanothreads about 6.4 angstroms wide, and they're mainly sp cubed carbon. Now, here is Arthur C. Clarke in The Fountains of Paradise. So he writes, so you have one person tells another, you have an invisible wire. And he says, what is it? The result of 200 years of solid-state physics, whatever good that it does, it is a continuous pseudo one-dimensional crystal, although it's not actually pure carbon. It's going to throw some things in order to make it stronger. Well, this is pretty close to this stuff, so you can imagine. So what's out on the internet? On the internet is a dearth of content, okay? That's one way to characterize what's there. And there are lots of hucksters, people anxious to hype things, to sell them to venture capitalists and so on. They had a good time with nanotubes for a few years, but then people got tired, and now people are making use of nanotubes, so not quite to the degree of hype that accompanied them initially. up comes the hype level again. Now we have this material, just like Arthur Clarke predicted, that is going to save the world. And so venture capitalists are beating on the door of the Penn State people. When are you going to start a company to make this stuff? In order to build from these things an elevator up to space. That is the idea. Now, meanwhile, in the literature, there had been 3 suggestions of saturated benzene nanothreads of this type. Vin Crespi in 2001, in a paper we missed when we published on this 10 years later, suggested this structure, and here you see clearly for chemists the chair cyclohexane rings in this, with 3 axial positions up, 3 axial positions down. The price you pay for that arrangement, which is very nice, is eclipsing. This is a piece cut out from the hexagonal diamond structure and has both cyclohexane rings in it. We looked at we had a paper on a compression of benzene, on what happens to benzene under pressure. And in that paper, by chance, we found a polymer, a one-dimensional polymer at a much higher pressure that we predicted might come out from compressing benzene. This is a little more difficult to see, but you can see here a benzene ring, then another benzene ring, and another one. And there are sometimes linkages of 2, sometimes of 4. You can see this in various ways. We called it polymer 1. Dirk Trauner, a very good organic chemist with biomolecular leanings, he has a sightline in twistane. Twistane is a hydrocarbon here in which every cyclohexane ring is not chair and not boat, but twist. And you have to build a model to believe it. But he postulated, he actually has made oligomers of these. And he postulated an infinite polymer like this in one of his papers, in which every ring is 6-membered. You notice in this one there are some 5-membered rings here. But here they're 6-membered, but every one is in a twist boat form. So these were in the literature before. So what are the nanothreads? Right now, the situation is there is much more progress on the diffraction patterns, and are very interesting X-ray diffraction patterns, which clearly indicate an ordered stacking of these threads in a hexagonal crystal, which is what you'd expect of these threads, but they are disordered within each thread. So the best model right now, I know the one way to define theoreticians they are the community, the subcommunity of our community, which wants the world most simple. Okay, so we want them. We calculated these. The world gives us a mess. I mean, not quite a mess, a partially ordered mess. And that's very interesting. So what the nanothreads are right now best fitted as is one-dimensional polymers which are disordered along the polymer with regions which partake of some of these other polymers. And however, there are tantalizing suggestions of ordered regions. So I don't think that it's out of the question that just like people learned how to make nanotubes of a given diameter and chirality, a fascinating story which I don't have time to tell you, that people will learn how to make these of a given one of these structures that we suggested. So what Vin and his co-workers did, and Shishu and a colleague Lammert, is they systematically enumerated there is an infinity, so you have to limit yourself. Isomerism rears its ugly and beautiful head along the way here. There are many different isomers, and here are the three among them. The one he predicted earlier, our polymer 1, and here is Trauner's polytwistane, which actually emerges as the lowest in energy. These are the 15 lowest in energy of the infinity found so far of the various nanothreads that they have calculated, and they did this. So this is where we came in, not quite yet, because there was a mechanism proposed. Of course, people propose mechanisms for how these threads are formed. And one mechanism was that you do in the benzene crystal a sequence of Diels-Alder reactions to give this polymer over here. And then that polymer can be zipped up. If you could do a 2+2 reaction on this, you could go 1 to 1 and 2 to and 1 to 1 and 2 down. You don't want to end the polymer, so you don't want to go up both of these and form a cyclobutane here. But you can zip it up in this way, or you could zip it up in a slightly different way. And eventually, actually, you can get all of the nanothreads. Now, at this point, one naturally wants to look at the benzene crystal. What does the crystal, what constraints does the crystal offer in this? Because this is a solid state reaction. You're doing this, that benzene is a liquid doesn't matter here. Everything goes solid under pressure. So the benzene goes solid here. This is the benzene crystal, and there are stacks in it. Oh, incidentally, this is a 3D model. You can build this. So the black, what are the black things are not bonds. They're struts to hold the model together. So this is a problem you have to face. When you build a 3D model of a molecular crystal and the molecules are apart, you got to hold them together somehow. And you have to figure that out. That's what we figured out. This is coming. There's another story in here which I will allude to a little bit tonight in something else. There are stacks in these. Stacks are in the eyes of the beholder. There are stacks there. Human beings are made to lie down and see clouds in the sky as animals, okay? What I'm trying to say is we are pattern recognition machines, and we see patterns where there ain't any. Stacks are this, there are stacks everywhere in a lattice because it's an ordered array. You can look down any one of the Miller indices and you can see a stack down there. But some stacks are better than others and can lead to something. Anyway, what we thought we would do, Bu Chen and I, and joined by these other people, is to try to provide a roadmap for the polymerization. The Penn State people had enumerated these. We thought that along the way there surely must be polymers with, it's not all going to happen in one fell swoop. You can be sure about that. And even this is naive because the polymerization, no doubt, is nucleated. It starts out at some radical site that's being formed. So a question of how does the polymerization take place. But we thought what we could do is to provide a roadmap for going from this to that by constructing all the possible isomers, possibilities for polymers along the way, which had, if you call the 0 degree of saturation, and this 6, the ones with 2 and 4. And why didn't we do 3 and 5? Because those are radicals. And we were looking here for the stable waypoints in this. So how to enumerate these? So you start to do this, and it's lots of fun. And it brings up lots of things from organic chemistry. For instance, here are the building blocks of the degree 2 polymers. So degree 2 means everything that was a benzene ring retains 2 double bonds. Just 2 are saturated. So the 2 that are saturated can go off 1 to the next unit, 1 down. So here is what they will not do. They will not both go up, because that's the end of the world. The polymer doesn't go on if they both go up. We want an infinite polymer. So 1 has to go up, 1 down. But you recognize this as you look at it, that this is chiral. It's got a twofold axis. So there is a mirror image of it. That's O minus. O for ortho, nothing fancy here. Or you can go para, which is not chiral. So those are the building blocks. Now you combine these to the next unit down. So you can build a polymer from all paras. You can build it from all ortho plus. But the polymer that you build from O ortho plus and ortho minus is not the same polymer as you build from all ortho plus. You've probably forgotten 3O and erythro, but this is the same story here coming up here. This is organic isomerism, the most beautiful thing in the world in some ways. Here are all the possibilities for 3 units. So how many isomers are there in all of such polymers? The answer is an infinite number, because there is, you can have any choice. So you have to stop. And so this is an interesting story about what nature seems to go out of absolute order, the highest order, but doesn't go to the lowest order. We could talk about that. To the lowest symmetry often, but stops in between. So maybe some other repeat units. Okay, we start to generate these. Let's show you. Here's PO plus. You see, this is O para on this benzene ring, O on this one, para on this one. Now, these all, at first glance, they look all the same. I assure you they are not the same. They are isomers of each other. Isomers, constitutional isomers, in the sense you're going to have to break bonds to bring one into the other. These are not optical isomers. These are not geometrical isomers. They are not conformations. They're real isomers. Here is one, para, ortho, and then this is para, and then there are 2, so it's 2 paras and an ortho coming together. Anyway, these are 4 of the 8 isomers, and there are conformers that we have found. For the ones with degree of saturation 4, what does that mean? It means each benzene, what was a benzene ring, retains 1 double bond only. Turns out there are building blocks are 4, and you cannot have, this stands for up and down. There are no fancy Latin words here. These are just Anglo-Saxon simple denominators. Here, 2 up, 2 down. That's what goes on here. What you cannot have is 4 up or 4 down, because 4 up, 4 down ends the polymer. Okay, so you have to have 2 up, 2 down, or you have to have 3 and 1. These are 4 chiral pairs plus 1 achiral one. And from these, you have to stop at a certain number of units. You can build a substantial number. And here that we came into a thing of isomerism, which helped us actually, because now we really didn't, at this point we were getting tired. There were too many isomers to write down. No one was going to read this paper. So, but here something helps a little bit. here are two isomers. You can see that this is formed at each benzene ring by 2 down and 2 up. Okay? 2 down and 2 up, but different in the 2 rings. You get this, and this is another form, and these are, this one, they're really similar, but this one puts the double bonds on one side, and this one the double bonds on the other side. Let me show you the polymers, actually. Here's a form. This is actually the polymer that happens from a Diels-Alder reaction of benzenes to each other. All the double bonds are on one side. Here, one double bond is here, another one is here, another one is here, another one is here. And in this one, some other possibility. When I saw this, I was very happy. It allowed me to use this little marker, which means dead end. And because what this means, that's a very nice isomer, but it's not going to go on to a nanothread because it can't, that double bond can't react with that one in a further polymerization. It can lead to cross-linking, which is a problem for me, but it cannot lead to a further polymer. So here are 23 isomeric degree 4 polymers with a topological repeat unit of only 2 benzenes. And you can see lots of interesting things. You can see helices beginning to form. You can have helices with irrational pitch, which is a real headache, meaning that they don't repeat a certain number of units in one turn of the helix. But 16 of them have got a little marker on it. That little marker says they can't go on to the degree 6 nanothreads. So they are dead ends. That's very nice for us. And here is Boo's roadmap. This is a major achievement of isomer enumeration in a polymer. And what we show is that the 15 lowest energy degree nanothreads, there are certain nomenclature for them, can be formed from 7 of the 23, which are not the dead ends of the degree 4, which in turn can be formed from only 4 of the 8 degree 2. Degree 2 of saturation, yes. And we now, so here is what it's not. This is a map of A to B to C by such and such a process, in enumerating the cycloadditions that are involved. It is not, there are no barriers. We have computed this. There are no barriers. And the process may be initiated and catalyzed, but this is what our paper is about. And that's essentially the first story that I want to tell you, except we're going on to look at some of the initiation steps. Here is that, and we are using here another trick. So this polymerization is taking place under pressure. We actually don't know where it's taking place as you go back from 20 gigapascals to 0 to 1 atmosphere. At what pressure does it start to polymerize? But it looks to be near the high end from the visual appearance of the material of that pressure. And what we have done here is we have put 2 benzenes here inside a helium compression chamber. So this is a theoretical torture device. So what's done is the 2 benzenes are put in there, and then they're put in about 100 helium atoms. Why did we choose helium atoms? Because helium atoms are the atoms I would think of as least reacting with a benzene in this world. They're a solvent here. The helium atom, they're put inside the box in a computer, and that box is repeated an infinite number of times with periodic boundary conditions, and we do our standard solid-state calculation on that chamber, and the volume of the box is what controls the pressure. The volume is large, the pressure is small, the volume gets smaller. The relationship dE dV is the pressure, allows us to get the pressure. So what we are doing is studying this reaction inside this helium compression chamber. As you see at the top, they're coming together. There's a transition state forming. Is that transition state different from what it is in the gas phase in this very non-interacting solvent? It's basically a solvent, but it's a very non-interacting solvent, but it's a solvent we put in for our theoretical reasons. So that's what we're studying. The last thing I wanted to show you on this is the energetics, because maybe it'll come to something I'll say at the very end, maybe I won't get there. Here is benzene. There's some energy scale, and why am I putting benzene? This is in electron volts, and it is the energy of two benzenes relative. There's some energy zero, which I haven't told you about, which is a molecule called graphene. And graphene is, I'm not going to hide the secret, graphene is graphene, a hexagonal sheet of carbon atoms, saturated hydrogen top and bottom. But what you see here is that here is the dimer of benzene. This is the energy units here are electron volts. So the translation is 23 kilocalories is 1 electron volt. So about 50 kilocalories, 40 kilocalories above benzene is the dimer, the lowest energy dimer of benzene, which happens to be the diazoyl product. The degree 2 polymers are all more stable per C6H6 than that. As you go to degree 4 polymers, they are more stable still. And when you go to the Rio nanothreads, they are more stable, and they are more stable than benzene. What is going on here? And I actually believe this number. So one of the things that's going on here can be summarized by this equation, which is not a theoretician's dream. 3 ethylenes going to a cyclohexane. I'll put in the hydrogens in here in case there are any physicists in the audience who... My daughter has a PhD in physics, but I love to make fun of physicists. This reaction is exothermic. This is not a theoretic number. It's minus 67 kcal per mole. So what's happening in that reaction? Relatively strain-free molecule, ethylene, is going into a strain-free molecule, you think, cyclohexane. And what's converting is 3 pi bonds are being converted into 3 sigma bonds. That's downhill by 25 kcal a pi bond. Sigma bonds are always more stable than pi bonds. Unsaturation really hurts thermodynamically, and chemists know this in another way. Acetylenes are high-energy materials. From acetylenes, you can make double bonds, you can make single bonds. To go the other way around, you have to put in some work, some driving force. So that's part of what's happening here. And why doesn't that curve keep going up? Because there is such a thing as aromaticity. And benzene really is more stable than cyclohexatriene, the archetypical oligomer here, the monomer with localized double bonds. Okay, now we go on to the second topic. Just Nothing to do with the first topic, except for carbon. And we're going to talk about something which are called clathrates. Now, I heard about clathrates because I worked in a crystallographic group with Bill Lipscomb. I heard about clathrates in graduate school. I saw them. I thought I understood them a little, but I really didn't. And what's at work here is just geometrical complexity. But clathrates are fairly complicated materials. And until 2 years ago, I did not really understand clathrates in the sense that they were in my mind in their full three-dimensional beauty. And I'm basically a teacher, so if I understand something, I think I know how to explain it to you. So let's start about that. This is another paper in JCS, a totally different group. Actually, one of them from Carnegie Institution of Washington prompted the problem, Tim Strobel. But this is the work of Tao Zheng, who was a postdoc then, is now an assistant professor at Carleton University in Ottawa. Clathrates are a generic term for things that somehow hold other things, form cage-like structures. You can form them from many things. This one happens to be formed, I think, from urea, but holds some organic molecule. The best-known clathrates are those that involve water as the building block, and which hold inside, in particular, the one that's best known as methane. These are the methane, but they also hold other things, chlorine, small organic molecules, hydrogen, a few hydrogen molecules. You see here the water molecules arranged, and each water molecule forms two bonds, real bonds, and then the orange ones are the hydrogen bonds, approximately along tetrahedral directions, and that's the key. And you notice that once in a while there's something sticking out. And if there isn't something sticking out, there is a lone pair sticking out that you don't see that's capable of forming a hydrogen bond. Basically, clathrates are things that are built up from things that want to point in four directions approximately in a tetrahedron. And this polyhedron, so what is this polyhedron? It's a dodecahedron. It's a class, one of the Platonic polyhedra. That allows it. The angles are exactly 108 degrees. That's not too far from the tetrahedral angle, just 1.5 degrees off. So you could easily take up the strain. And this is one of these. I'll show you this. We'll build this one up in a while. But first, I want to show you the methane clathrate, because we're going to hear a lot more about this because of environmental concerns about these materials. This is the stable form of water and methane at near 0 degrees C, below about 3,000 meters or so, when the pressure goes up. So under pressure, at the cold temperature, this is the stable form, and one of the forms has this precise stoichiometry. There is another form of 8 methanes and 46 waters. And with stuff, when you fish it out, it's dirty, but when you clean it up, it does look like ice. It looks just like ice. But there is something it does that ice doesn't. When you put a match next to it, it bursts into flame. And of course, it's not the water burning. Water is burnt. It's the methane burning that's being released here as it's slowly being released. And since methane is a greenhouse gas, there's a lot of concern about this being released. The story of the clathrate structures is a wonderful structural story involving several groups, a lot of competition around 1950, 52. Pauling is involved and Marsh in this, misspelled Marsh here. That's an interesting story I don't have time to tell you. The clathrates came back into attention around the period 65 to 69, when two groups, Hagenmüller in France and Harald Schäfer in Germany, made a number of clathrates from group 14 elements other than carbon, like silicon, germanium, tin. There's a listing of many of them, but this is an archetypical composition. And just like you had 8 methanes and 46 waters, now you've got 8 bariums and 46 silicons. The silicons take the place of the water at the vertices of the clathrate, and the bariums are in the center of them, one filling every polyhedron that you've got around. So now let's talk about the two most common clathrates. These are called clathrate 1 and clathrate 2. The conventional unit cells of these have 46 and 134 atoms in them. They are not simple, and yet they are cubic. And they are very interesting. But I can build these up for you. That there are only, for this clathrate 1, there is only 2 building blocks. One is the dodecahedron that everyone can visualize, especially if they've played Dungeons and Dragons, because the dice come in that form. The other polyhedron that's in there is one which is called 5, 12, 12 pentagons, and 2 hexagons. Here are the hexagon beneath. The 2 hexagons are linked by a chain of 12, by a belt of 12 pentagons. Why does one need that? The reason is that you cannot fill space with perfect dodecahedra. If you try to do this, you get into the same trouble as when you try to pave your bathroom floor with perfect pentagons. It would be nice, and they're so damn close. 108 degrees is pretty close to 120, what you need in a bathroom floor. Here, it's even closer. The angles are 108 for 3 of them. And that's close to 109.5, but it's not enough. You get little nooks and crannies left over. And if you mix some of these guys with some of these guys, you don't get perfection. I'll show you how slightly imperfect they are in just a moment, but you get close to it. And now they're mixed in a certain admixture. You see these dodecahedra are at the vertices of a simple cube. So there are 8 of these shared with 8 unit cells. That's 1. Then there's 1 in the middle. You can't see it, except you can sort of see it through the middle. So there are 2 dodecahedra per unit cell. And you see these 2 here, the 2 of these guys sharing a 6 face. That's how they are sharing each other. There are 2 of these per face of the cube. You can see them in the front face. You can see the 2 in the top face, the 2 in the side face. So there are 12 of these divided by 2 unit cells sharing them. So there are 6 of those. So in the unit cell of this, there are 2 dodecahedra and 6 of the other kind of polyhedra. This one, clathrate 2, has as building blocks only this and another weird polyhedron, which has 4 hexagons. It's 5, 12, 6, 4. It's very explicit notation here, what it is. It's got 4 6-membered rings. Here you see one of them. The other 3 describe a tetrahedron, and the things in between them are pentagons. These 2, this one and that one, believe me, build that one in this way. And a model helps a lot. This is the best we can do without a model. So what are commonly called clathrate structures self-assemble everywhere in nature where space is to be filled with something that is four-coordinate and wants to be tetrahedral. Now that something, the node, can be water, where the four directions are two bonds and two lone paired hydrogen bonding direction, can be a silicon or a germanium. It could be something else also, but these are the ones that are known. They could also be what we're talking about as zeolites. These are silicon dioxide as the building block of these things. Okay, so now if silicon can do it, not only silicon but germanium and tin, as you can see, why not carbon? Why should carbon be left out of this game? Okay, there's a good reason. So carbon has two good things going for it, diamond and graphite. There is a story to be told about these. But if one tries to build, the question of why not carbon was asked by a former postdoc of mine, Reinhard Nesper, and he calculated for the clathrate structures what their energies would be if they were made out of carbon. And they come out not too bad. I'll show you what not too bad means in just a minute and why they are not too bad. But first here I show you what not too bad is. These are 5 clathrates. I've stressed these 2. Here are 3 other popular ones. There are about 17 types of these that have been identified. This one is particularly easy. This is called sodalite. And it has this polyhedron with 4 and 6 membered rings in it. Very nice, 1 polyhedron. This is the only one which is built up of 1 polyhedron. The others all have, ubiquitous in them is the 512 one. So here are 5 of these 5 over here. And here in the calculation, which you can believe or not, but there are other calculations as well. These are the energies, the relative enthalpy per carbon atom relative to diamond. Okay, so these are all unstable relative to diamond. But the best one, clathrate 2, is only 0.08 of an eV per carbon atom unstable relative to diamond. And once made, it's not going to rearrange to diamond any more than diamond rearranges to graphite once it's made, even though it's slightly thermodynamically unstable relative to graphite. So that, because you have to break bonds. And the other thing that comes in here is Buckminster fullerene, which has engendered a wonderful chemistry and physics. That is it's a moderately strained molecule. It's not a very strained molecule. But if you translate that, because of the non-planarity of the 3 bonds, it is 0.39 eV per carbon, and that is an experimental number. So if you want to heat your wood stove with Buckminster fullerene, you will get a brighter flame because it's less stable than if you heat it with coal. But it's a little expensive for doing it. Okay. So why are these things so close to diamond? The reason is that the clathrate structure does not require much distortion. Here is the range over all the angles in all the polyhedra and all the distances. And you see that these are distances, exception of one distance in clathrate 4. They are all pretty close to 1.53. And the angles, there are some 120-degree angles and some a little bigger, but not much, not terribly strained as these things go. So that's the reason why these are unstable, but still not so unstable. Okay, so now why not? Why can't? What's the trouble? The trouble is that organic chemists who can make any molecule in the world, I really do believe that. As far as making molecules to order in 2 or 3 dimensions, are not yet there. In 0 dimensions, that means discrete molecules, they can make anything. I really do believe. When I see something with 40 asymmetric centers made, I really believe. In 1 dimension, we have polymer chemists who can make anything. Also, just about. You want a polyblock thing with 1 block of polyethylene, 1 block of a terephthalate, something else, they'll make it for you. They can do that. But in 2 or 3 dimensions, it's hard. There is little control. So that what we thought was, maybe just like this one exists, I forgot to tell you that the silicon-only clathrate does not exist, or did not at first. It actually has been made now. But it was hard to make. The barium somehow nucleated the formation of the clathrate around it. Now, this is another story. That is how people make zeolites. So people make zeolites by taking an organic molecule, condensing silica around it, and then burning away the organic molecule in the middle. So we're not going to quite do that, but maybe could we make something with something in each carbon polyhedron, which is stabilizing it. So in this beautiful paper by Kartunen and Fessler, they looked at every one of the building blocks of the zeolites, and they calculated and compared with experiment the guessed that center to vertex distance of every one of these polyhedra. They're essentially calculating how much room there is inside. And if you take silicon with a silicon single bond distance of 2.35, you find that the center to vertex distance is 3.2. That's pretty big in the middle. That's big enough for, it's big enough for barium, as you saw. It's big enough for barium. And barium is pretty big. It's big enough for anything smaller than barium, too. But if you do, and the same goes for germanium, and look what happens with carbon. So here's the difference. The block outside, the clathrate, is made out of all single bonds. That single bonds are 2.35 for silicon, but are 1.54 for carbon. And the size inside the box for carbon is around 2 angstroms inside the dodecahedron. And that is not good news. That's too little for even the smallest atom. A lithium, a helium even has trouble, but helium might just fit in, but helium is not interesting in this chemical context. Lithium and beryllium are too large to fit into that cage. But we thought maybe we could put in lithium plus. But then we got to balance the charge. Yeah, lithium plus is very small. Beryllium 2 plus is even smaller. So maybe lithium plus or beryllium plus could go in. But then we've got to have a minus. You could put a counter ion outside, but there ain't no outside here. It's just that there's no room to put an anion in the next cage over. So what we did was the obvious thing a chemist would do, And that is, take this carbon and replace a few carbons by borons. Because what that does, also the size of a boron is not that different from that of a carbon. So what that does, these are isoelectronic molecules, ammonium, methane, and borohydride. And you can see here, every time you take a C and you put a B in it, but you make it form 4 bonds, it's got to be a B minus. So what we're going to do is to form, as you see, how many borons are we going to make? As many borons as we put lithiums in the middle. So what we've got to do is to dope the outside of the clathrate with some borons in it. This is nothing sophisticated. This is just isoelectronic replacement in here. And we calculated all 5 of these in excruciating detail in this paper. And here, I tell you, you can't get away from isomerism. It's the most chemical thing, and it's everywhere you look. You saw it in the benzene nanothreads. I had many isomers. Where's the isomerism here? I've got to, in the sodalite cage, the simple one, I've got to replace, I put 2 lithiums inside the cages, and then I've got to put 2 borons outside. But there are 12 carbons in the unit cell. So I've got to replace 2 of the carbons with borons. So there turns out there are 5 ways to do this. This is isomerism again. Now, that's easy. Now, imagine clathrate 1 with 46 carbons. And I've got to replace 8 of those carbons, and precisely 8 with borons. There is, you can do the combinatorics as well as I can. There is a very large number of ways to do this. We tried everything. We tried saying, let's choose the highest symmetry structure. Let's choose to substitute the weakest bonds, or the small charge that is developing in the skeleton itself. In the end, we gave up, and I think when these things are made, these are also going to be amorphous. They're going to be solid, but they're going to be mixtures of a variety of isomers of these. So here is the end of a story in this paper, and that is, here was the energies of the 5 clathrates with nothing in the middle. When you stuffed them with lithium atoms, I told you there was no room for them, but theoreticians can do tortures on molecules. There's no problem. We stick them in, we calculate, and the molecule tells us it's 2.3 eV per lithium higher in energy. It doesn't like it. So then we put in 8 lithiums in the middle, but put also 8 borons in a changer around, and the electron jumps from the lithium to the boron. And these are, the energies are not so bad, but under pressure, and this is what interests us, these things become substantially exothermic. I haven't told you why under pressure they're exothermic. It's a little subtle. But we think that these are a good candidate for high-pressure syntheses. So that's the 2 stories. But I have 3 minutes. Is that yours or mine? Oh, I left mine in a hotel, so it can't be mine. Okay, I have 3 minutes. I want to tell you a little bit of another story that's connected to this. I told you that because this is a story about philosophy of organic chemistry. I told you that the stable point for benzene was not benzene, but graphene. What graphene, as I told you, is graphene plus 1 hydrogen per carbon. Turns out that there, isomerism, again, there is not one that is the most stable graphene, where 3 of the 6-membered ring carbons, 1, 3, and 5, get hydrogenated from top and 3 from bottom. But there are other ones that are not that bad. And all 4 of these are more stable than benzene. Now, This is a hard thing for organic chemists to get used to, that there should be anything more stable than benzene. But this is part because we're leaving with this beautiful mythology of the benzene molecule. You get a little bit of a correction to that mythology if you go in a NIST Web Book of Chemistry where you have thermodynamic data and you look at the heats of formation. So the heats of formation of methane, of cyclohexane, of ethane, those are all negative. That is, it's downhill from the elements to the molecule. But the heat of formation of benzene is plus 15 kilocalories per mole. It's positive. So it is stable. It's very stable relative to these things, but it's not so. Let me try to convince organic chemists in the audience why you should believe that graphene is more stable than benzene without doing any calculations. So let's do a Gedanken experiment. We take a bunch of benzenes and line them up like that in a plane, okay? That's going to take a lot of entropy, but that's in the free energy. That's not in the enthalpy. So we're going to worry only about the energy. Yes, there's a big entropy factor. Then we're going to de-aromatize every last one of those benzenes. This is all, I told you this was a Gedanken experiment. We're just thinking about it. So how much does that cost? Well, this is a remarkably difficult number to get, but everyone here would probably come up with some number like 40 or 50 for kilocalories for the aromaticity of a benzene molecule. And so let's take that number, 40 or 50, okay? Then we go from here to here. From here to here is a bunch of double bonds, 3 double bonds going to cyclohexane. I wrote it out for you. And that's an experimental number. So that the downhill that you get from forming the single bonds is more than the uphill that you pay to de-aromatize. So that's why this reaction as a whole, now you do a Born-Haber type thing, this reaction as a whole is exothermic. Okay. Now let's look at this story a little bit wider. Let's look at for other compositions. What's the most stable form of carbon? It's graphite or diamond. Okay. What's the most stable form of the composition CH? No, it's not acetylene. And no, it's not benzene, it's graphene. That's what I've just convinced you. Let's go on. CH2. No, it's not ethylene. Cyclohexane? Maybe. Actually, polyethylene is thermodynamically slightly more stable per CH2. They're both composition CH2. We're talking about an infinite, all crystalline polyethylene, a single chain, but you could do it for the solid, the crystal. That is a very small number, but before you go, if you have trouble falling asleep tonight, you can think about why cyclohexane is actually slightly strained. I'm not going to talk to you about that. So let's take the next one. Ethane and methane are the most stable forms of CH3 and CH4. But actually, no. Because the reaction to give methane plus C from all of these, I've taught freshman chemistry, so I know how to balance equations. I know I need 4 hydrogens. I need 3 carbons on that side. I can put them in. It's not going to make any difference to the heat of formation. Graphene or benzene going to methane plus carbon in the right mixture is exothermic. So is polyethylene. So is ethane. The only compound stable thermodynamically in the carbon-hydrogen system is methane. Very interesting. Well, let's forget about that for a while. Go back to that. What about these simple ones? Nitrogen, the most stable form is N2, or crystal of N2. CO2, CO2. The really interesting one is CO. CO is, we know, thermodynamically unstable relative to CO2, but it's actually not. A crystal of diatomic CO molecules, this thing here, is not the most stable form of the composition CO. And it's the same story as here, that if you can go from the triple bond of CO to saturated structures which have 4-coordinate carbon and 2-coordinate oxygen, you will be going downhill in energy according to calculations. And here are 2 such structures which are already in the literature. These 2 over here. Nobody has made these. So now this is the last slide, I promise. So here, let's see. Let me say it another way. The things that are in black here are 19th century or earlier. Those are the molecules we've had. They are our heritage, precious, interesting molecules. The ones that are in green are the only new thing in the whole of the 20th century that has been brought to the table in this particular little subfield of chemistry. Very small subfield. And the green ones are going to be the 21st century. They're waiting for the young people in the audience to figure out ways how to make them. Thank you. Any questions about anything? Yes?
The slides there. You convinced us that formation of cyclohexane from ethylene is exothermic.
Yeah.
How come N2 doesn't trimerize now it's what?
It just, the balance is not there. So let's, N2, even the striking thing is, the isoelectronic series, the trimerization of ethylene to give benzene is highly exothermic by over 100, maybe over 200 kilocalories that way. But for N2, this thing here with 6 nitrogens probably does not. There is a dispute in theoretical chemistry community whether that's a local minimum. But this is downhill by 200 EV, 200 kilocalories in that direction. Nitrogen is special. It remains, however, at high pressure, people have made a form of nitrogen which resembles that of antimony and arsenic under it in the periodic table, a 3-coordinate net with nitrogen, 3-coordinate with lone pairs. But under normal pressure, I don't have a simple answer to that. That's a good question. Back there.
I was wondering, what is the relationship between clathrate and zeolites? Are clathrates like a subset of them, or?
Yes, so nomenclatures in chemistry are very fuzzy sometimes. Purpose of UPAC is to try to make up definitions. They're always behind. And when they get up with a definition, there always are holes in the definition as well. So both of these in general, I would say that clathrates are the wider category and encompass zeolites. Zeolites are aluminosilicate clathrate structures. The basic building block is is the silica building block, which is the same 4-coordinate node, now 4 SiO bonds going off tetrahedrally. Now, when a few of the silicons are substituted by aluminums, just like I substituted carbon by boron, there is a negative site created there that is balanced in the zeolites by something positive, typically an alkali metal ion, but could be hydronium, sitting in the pore of the zeolite near the aluminum site maybe, or somewhere there. The great utility of zeolites is that the pores are big enough to encompass, in addition to the balancing ion, the sodium ion typically in a zeolite, to encompass organic molecules and sometimes pairs of organic molecules. And then things go in very constrained geometries, and reactions are then catalyzed by, at the least, by reducing the entropy, but maybe by electrostatic factors as well. Whereas the clathrates, so zeolites are clathrates, but clathrates are not zeolites in general. Not a very strict definition. Yes?
Other compounds that you can imagine forming nanorods, and one of cyclopentadiene, which forms a teal soda around it.
Yeah,
At room temperature.
that's right, very easily. So the Penn State people have tried so far, in their inability to functionalize because they can't dissolve the things, they've tried the halobenzene so far, no great luck, and they have tried pyridine and some other things. I've advised them to do post-functionalization. In polymer chemistry, you can do that. You can take a polymer, and then this is like post-translational in biological things. You can make the polymer, and then you can do chemistry on it. And that's actually commercially viable for some things. And there are ways to knock off the hydrogens from those tertiary positions that are there.
They haven't tried cyclopentadiene.
They haven't tried cyclopentadiene. Someone else has. We have actually calculated that dimerization, exo and endo. It's one of our prototypes in that helium compression chamber, so we're interested in it.
And diluting the benzene with a little bit of toluene, would that knock out the...
Don't know. The structures are similar. There are also these herringbone structures with stacks. So my realistic picture, I'm a theoretician, I love these calculations, but realistically what I think is that badly formed crystals of benzene form, and under compression, either going up, but I think actually going down, there is cracking, there is little local heating. I once had the misfortune of condensing some acetylene in a gas tap, and no one told me that you had to I heated it up fast, and I got an explosion. I actually did some experimental work, this Bureau of Standards. Anyway, there is local heating. I think what's generated is some initial bond formation to give a diradical between two benzenes, and then it goes on in some way. It's local. Still, the stacking may constrain the thing to go in one dimension rather than to go sideways. So you don't, this is not an isotactic, this is not a single crystal to single crystal transformation. It's not going to happen that way.
Thank you, Professor Hoffman.
Thank you.